Okay, so in the last video, I was talking about this ALEKS topic, writing the rate law implied by a simple mechanism. And in the first video, the first step is much slower than the second. So this is I guess the most common version of this question that you're gonna get, but it was also sort of drawn to my attention that there's another version that's much more complicated that we should also talk about. So this is the other version, and in this version, the first step is much faster than the second. So we need to, when we're doing this topic, we need to identify which version we have. The first version, where the first step is much slower, it's a little bit simpler. It's easier for us to solve that problem. It's a bit more straightforward. And this version is much more complicated. So I'm gonna walk us through this one and hopefully answer all the questions that we might have. So the first thing is the same, write the balanced chemical equation. So let's go ahead and do that really quickly. The F gas, that's going to be my intermediate. It's formed in the first step, it's consumed in the second step. So I can write out my full balanced chemical equation is going to be 2NO2 gas plus F2 gas goes to 2NO2F. So this is my reactants and this is my products. And this is a balanced chemical equation. I've got 2 moles of nitrogen, so on and so forth. We can see that. Now, for the next part, it says write the experimentally observable rate law for the overall chemical reaction, and then it says your answer should not contain the concentrations of any intermediates. So if we go back and we sort of say, well, if K1 is much greater than K2, that's telling us that this first step of the reaction is really fast. That means that the second step is our slow step. And if I wanted to write the rate for that slow step, that's going to be equal to K2 times the concentration of F times the concentration of NO2. So this would be my rate law for my slow step, and previously in all the other examples we've looked at, this is going to be the rate law for the overall reaction. Now the problem with that for this type of problem is that we have an intermediate in our slow step, and this tells us it should not contain any intermediates. So we need to sort of deal with that somehow. We need to get rid of that. And the way that we're going to get rid of that is we're going to use this information from the first step. And one thing I don't like about this problem is that this first step should really be shown as an equilibrium. If the first step is a fast step, that usually means that it's a fast equilibrium, and that's a key bit of information to solving this problem that's not really given to you. So I don't really like that aspect, but let's go ahead and continue. So if that is true, then the forward reaction we're going to call K1, and the reverse reaction we're going to call K to the minus 1. So it sort of refers to that later on as well. So what we can do is we can say in the forward reaction, so this is for step 1, the forward reaction is going to be R equals K1 times NO2 times F2, right? So that's just writing out the forward reaction. The reverse reaction is going to be R equals K to the minus 1, and then really my products, NO2F and F. So this is writing for the reverse reaction going right to left. This would be my sort of rate law for that. And then because I sort of said that this is at equilibrium, the key for this problem is that then these should be equal to each other. Equal when at equilibrium. So if you're at equilibrium, these two rates should be equal to one another, and we could then write K1 times NO2 times F2 will be equal to K to the minus 1 NO2F times F. So this is the key bit of information that's sort of missing to help us solve this problem. So for this section here, now it says write the experimentally observable rate law. We know that that's going to be based off of our slow step, but the problem with this is that it includes this intermediate. And we want to be able to get rid of that and only write our rate law in terms of things that show up in the overall chemical reaction. It's okay if they're reactants or products, but everything in our rate law needs to be in terms of things that are in our overall chemical reaction. So if I say that R, my rate, is going to equal K2 times F times NO2, what I want to do is I want to substitute out this F for some other terms that are in my overall reaction. So I'm going to take this bit of information where I said that my two steps are going to be equal to one another. The forward reaction is going to equal the rate of the reverse reaction. And I'm going to rearrange the information here to solve for the intermediates, to solve for F. So I'm going to take this information and I'll just sort of bring it down here. And I'm going to start rearranging things. So I'm going to just leave F on that side and sort of bring everything else over to the other side. So I will end up with K1 over K inverse 1, so just dividing both sides by K to the minus 1, times the concentration of NO2 F2 divided by the concentration of NO2 F. So that's going to all equal my concentration of just F. So this is just rearranging all of this. And now I'm going to take this equation and I'm going to substitute this into my big rate law over here, where this F term right here is going to be substitute for all of this information. So now I can say that the rate is going to be equal to K2 times K1 over K inverse 1 times the concentration of NO2. So now I'm just sort of writing all of this stuff out. F2 over NO2F. And then that's going to be multiplied by the concentration of NO2, right? So this F term here, this is all of this stuff here. I'm substituting all of that in for this. And then I've got my other bits right here and here. So now I can sort of simplify this and group this together. So my R equals K, so remember this is my overall K. So I'm going to group all of these together. And then this will end up being R equals, I'll write right here, K times the concentration of NO2 squared, right? So NO2 times NO2 times the concentration of F2 all over the concentration of NO2F. So now I've got everything in terms of things that show up in my overall reaction, my reactants and my products. So I've got reactants, I've got products, I've got my K here. And now for this bottom part, so I've grouped all of these K2, K1, K to the minus 1. Those are all constant. I've grouped them all together into this overall constant. And that's really the answer to the bottom question. So the answer to the bottom question, I'm going to write this K term in terms of all of these. So in this case, it's just going to be K2 times K1 over K to the minus 1. We could also just write that as K2, K1 over K to the minus 1. So that's what I would put in for my answer for this problem. So let's go ahead and review, just go back over everything that we did in this problem. The first thing, write the balanced chemical equation. That should be straightforward. That shouldn't be a problem. We've got our two steps. We're adding them together, grouping everything on the left-hand side, grouping everything on the right-hand side, canceling out our intermediates. The intermediate in this case is just this F gas. For step 2, this is where the more complicated aspect comes in. So in step 2, we're saying, well, if step 2 is a slow step, then the slow step, the rate of the slow step, that's going to be determining the rate of the overall reaction. So initially, I might write this K2 times F times NO2. That's the rate of the overall reaction. But the problem with that is we typically don't want to write the rate for the overall reaction with intermediates. So this says should not contain any intermediates. So we need to have a way of getting rid of that intermediate. The way that we do that is we assume that step 1 is what we would call a fast equilibrium. If it's a fast equilibrium, we can say that the rate of the forward reaction will be equal to the rate of the reverse reaction, and that we can sort of make this big, equation here where the K1 concentration NO2 times F2 is equal to K to the inverse 1 NO2F times F. I'm going to take that down here and rearrange everything and basically solve for the concentration of F, and then use this piece to insert into, right? I'm going to insert this into my rate law to substitute out for that intermediate. That gets me to here. Simplifying that, I'm going to group all of my constants together, and that's really the answer to the bottom part, grouping these constants together. And then simplifying this, just multiplying NO2 squared, that gets me this answer here. So I'll show you what I actually typed into ALEKS. So these are the answers that I actually typed in. just so you can see, what it looks like. I did check this, and it is the correct answer, so you can rest assured that I'm not lying to you here. But here you can see my simplified version of my rate, and then this k value here, right? That's really equal to this k2, k1 over k to the inverse 1, and we can see that, that's what we have here, k2, k1, k to the inverse 1. That's where I got that from. So, all right, hopefully that answers your questions. If you're still confused by this topic, let me know, and we'll talk about it a little bit more.